The overall goal of this procedure is the chemical synthesis of highly efficient organic materials for organic light-emitting diode applications from commercially available starting materials.
This method can help answer key questions in organic electronics about the use of thermally activated delayed fluorescence in lighting applications. The main advantage of this technique is that it uses readily available materials and is accessible to researchers with little experience in synthetic organic chemistry. Demonstrating the procedure will be Oleg Faborny, a PhD student from the Skabara research group and a member of the EXCILIGHT project.
To begin the synthesis of compound 4, in a 3-neck round-bottom flask, dissolve 0.80 grams of compound 1 and 0.45 grams of compound 3 in 250 milliliters of anhydrous toluene. Open a nitrogen source and connect to the reaction flask. Then, open up nitrogen valve and place a needle into the solution. Degas the mixture by bubbling nitrogen gas through the mixture for 15 minutes while stirring vigorously. Add 0.025 grams of palladium DBA and 0.06 grams of XPhos and degas the mixture for another 15 minutes while stirring.
The most critical step of the procedure is the addition of the palladium catalyst and XPhos followed by degassing for 15 minutes. This must be done quickly to avoid degradation of the chemicals in air by oxidation.
Next, add 0.32 grams of sodium tert butoxide and 6 milliliters of tert butanol and degas the mixture for 15 minutes. Then, put the mixture under a nitrogen atmosphere. Stir the degassed reaction mixture for 18 hours at 110 degrees Celsius. Check the completion of the reaction by looking at the solution with a UV lamp. When complete, the solution should glow with a blue light. Then, allow the mixture to cool to room temperature. Dilute the mixture with 150 milliliters of water and extract the product into 250 milliliters of DCM. Check the separation of the organic and aqueous layers by looking with a UV lamp. The organic layer should glow with a green light. Wash the organic layer with 150 milliliters of water twice. Dry the organic layer over 15 grams of magnesium sulfate. Filter the product mixture and remove the solvent under vacuum. Dissolve the residue in a 1-to-1 mixture by volume of DCM and petroleum ether. Purify the crude product by column chromatography. For easier purification, use a UV lamp. The solution of the compound should glow with a bright green light. Remove volatiles under vacuum to obtain compound 4 as a white solid. The resulting compound must glow with a blue light under the UV irradiation. To begin synthesizing compound 5, in a 250 milliliter 3-neck round-bottom flask, dissolve 0.67 grams of compound 3 and 0.75 grams of phenothiazine in 60 milliliters of anhydrous toluene. Degas the mixture by bubbling nitrogen gas for 15 minutes while stirring vigorously. Then, add 0.11 grams of palladium DBA and 0.12 grams of XPhos and degas the mixture for 15 minutes. Add 0.38 grams of sodium tert butoxide and degas the mixture for another 15 minutes. Then, under a nitrogen atmosphere, stir the reaction mixture for 18 hours at 110 degrees Celsius. Allow the mixture to cool to room temperature. Dilute the mixture with 150 milliliters of water, extract the product into 250 milliliters of DCM, and wash with 2 150 milliliter portions of water. Dry the organic layer over 15 grams of magnesium sulfate and filter the mixture. Remove the solvent under vacuum and dissolve the crude product in a 2-to-1 mixture by volume of DCM and hexanes. Purify the compound with column chromatography and remove volatiles to obtain compound 5 as a white solid, which glows with a green light under the UV irradiation. Toluene solution has an orange luminescence due to the solvatochromism. Two TADF emitters were prepared by a palladium-catalyzed amination cross-coupling reaction. Compound 4 was obtained in 63% yield, and compound 5 was obtained in 55% yield. Increasing the amounts of starting materials did not negatively impact the yields, suggesting that the reactions can be carried out on an even larger scale. The difference in photophysical properties between compounds is attributed to the different properties of the electron donating groups. Alkyl groups are introduced in the carboxyl units used in compound 4 to improve the compound's solubility in organic solvents. The synthesis of compound 5 uses commercially available phenothiazine without modifications.
After its development, this technique paved the way for non-chemist researchers in optoelectronics to become familiar with the preparation of these TADF emitters, which could help them investigate the potential lighting applications for these compounds.
Once mastered, the reaction can be set up in 1 hour if it's performed properly. The isolations of the product should take 3 hours.
Following this procedure, other palladium-catalyzed cross-coupling reactions can be performed to answer additional questions about the synthesis of TADF emitters. After watching this video, you should have a good idea of how to obtain and purify TADF emitters for further study.
While attempting this procedure, remember to carefully weigh the starting materials and degas the reaction mixture properly.
Don't forget that working with chemicals can be extremely hazardous. Please remember to follow all appropriate safety rules, including the use of a fume hood and personal protective equipment while performing this procedure.